Alright. So let's talk about nomenclature. Also remember no charges on compounds. So nomenclature. Naming for covalents with two elements, so binary naming. Name the first element with a prefix to indicate the number of atoms only if it is more than one. So we do not put mono on the first element. Name the second element using the prefix to indicate the number of atoms present. Drop the ending of the element name and they use IDE element or IDE ending. So just like ionic, we'll use IDE. But this time, because like carbon dioxide and carbon monoxide, they have the same elements, just different amounts. For covalent, there is no unique formula. You have to specify how many atoms there is. Well, this one's more complicated. If it was ionic, it would just be nitrogen chloride. You don't have to memorize the fact that you have to try means 3. So nitrogen and 3 chlorine, NCl3. Since nitrogen is only 1 and it's the first element, we don't use mono nitrogen, we put nitrogen trichloride. So for 1, it's mono. For 2, it's di. For 3, it's tri. For 4, it's tetra. 5 is penta. 6 is hexa. 7 is hepta. 8 is octa. 9 is non. And 10 is deca. So what would be the name of P2O5?
Phosphorus pentoxide?
Exactly. Diphosphorus pentoxide.
So why is 4 tetra and not quad?
Quad is Latin.
I thought
So
quadrilateral pentagon.
Greek versus Latin. Number of prefixes. So just to remind you, for 1, Greek is mono, Latin is una. For 2, di is Greek. We use Greek. Bi or do for Latin. They're both the same for 3, tri and tri. For 4 is tetra for Greek. Quart or quadra. I think quart is 1/4 though. And quad is 4. Penta versus quin. Hexa versus sect. Hepta or sept. Octo versus octa. 9, we don't use this one, we use non. And that's where November comes from, and October. December. Deca versus deci. Half is hemi versus semi. Poly versus multi. Hecto versus cent. Kilo versus milli. So we use that for like 1,000th. So what would be N2O?
Nitrogen monoxide?
Yes. It's also known as laughing gas. And sometimes they just call it nitrogen oxide, which is wrong. Its proper name is dinitrogen monoxide. SF6. Y'all know? Sulfur hexafluoride. Hexa being 6. What would be the formula for oxygen dichloride?
OCl2.
Dinitrogen trioxide?
N2O3.
And carbon monoxide. CO. I haven't been doing it, but I should have probably done Bohr model with these two. I've been doing just Lewis dot yesterday. We can also do Bohr model. So red is from the hydrogen, blue is from the carbon. You can see the Bohr model diagrams, and we ignore the inner shells because they don't matter. You can see on the orbital, the outer orbital for carbon now has 8. The outer orbital for hydrogen has 2. A single covalent bond occurs when atoms of some elements attain a noble gas configuration by sharing exactly one pair of electrons between two atoms. When drawing molecules, a line can represent a pair of shared electrons. So the Bohr model on the top, and the Lewis, I call it the Lewis dot method on the bottom. It's just a symbol. Oh, I'm thinking of the N adding this. Let's see if I can find the organic formula. Oh, you can't do it with CH4. I'm thinking about teaching you guys this notation. This is the most common way you see it. You can't do it with CH4, but a single line would be C2H6. A line with a bent is C3H6. This zig is C4H10. We'll learn this notation. It's really easy to learn. So if you have a pair that's shared, you can replace it with a single line. So if you have 2 dots on one side between them. Sometimes atoms share more than one pair of electrons between 2 atoms, creating multiple covalent bonds. When drawing these molecules, multiple lines can represent pairs of shared electrons. For example, diatomic oxygen, O2, and nitrogen have multiple bonds between them. So for oxygen, it's a double covalent bond in between them, whereas nitrogen is triple bonded. That's why nitrogen is so stable in our air. 80% of air is nitrogen. And that's the reason why N2 doesn't react with much. The triple bond is very, very, very stable. It takes a lot of energy to break those 2 atoms together because it has a triple bond. Oxygen is very stable too. However, if you get enough heat, eventually you'll be able to break it. So a single bond has 1 pair. A double bond has 2 pairs. And a triple bond has 3. So covalent bonds share electrons equally and unequally. Think of it as a tug of war between the electrons. Which molecule appears balanced and which one does not?
The one on the right is balanced.
Because they're two identical oxygens, they're going to pull equally on the electrons. Here we have oxygen bonding with two hydrogen atoms. The oxygen has way more pull than a single proton of each hydrogen. So oxygen is going to pull very strongly. This means that the oxygen atom is going to be more negative, while the two hydrogen atoms are more positive, because there is an imbalance in the sharing of electrons. Unequal sharing of electrons occurs when atoms that share electrons have different electronegativities. These are called polar bonds. Shared electrons spend a greater amount of time at the more electronegative atom. So, for example, in water, there is the oxygen is going to hold on to the electrons for longer, and they're going to spend more time on the oxygen, so the oxygen is negative while the hydrogen is positive. And these are only slight differences. This makes water a polar molecule because they have polar bonds. We'll use the Greek letter delta to represent Zent, because it's a partial positive. It's not fully positive or fully negative. It's only partial. So the hydrogen would have a delta plus charge, while the oxygen would have a delta negative charge. Partial charge. So, equal sharing of electrons occurs in nonpolar covalent bonds. There is no difference or very, very little difference in the electronegativity between the atoms that are sharing. Example, chlorine 2. Also CH4. Usually if it's this is actually carbon, CH4, methane. If the electronegativity is close enough to each other, it's going to be nonpolar. If they're far enough apart, it's nonpolar. Just because, here's an important thing, just because it has polar bonds does not mean it's a polar molecule. In order for it to be a polar molecule, it needs both polar bonds, so unequal sharing of electron, and it has to have the correct geometry. Meaning that if it's perfectly symmetrical, and no matter which way you rotate the atom or the molecule, it all looks the same. There is no side that's more positive than the other. For example, CH4. Even though these aren't polar bonds, if they were polar bonds, what side would be positive and what side would be negative? Well, hydrogen is all the way around it. So it all would have the same shape no matter how you rotated it. Whereas if you go to water, there's clearly a side that's positive and there's clearly a side that's negative. The top side here with the oxygen side is negative. The bottom side is positive. So it has polar bonds, and its shape is makes it so that it has one side that's negative, one side that's positive. So atoms bond according to the difference in their electronegativity. Look at the table of EM values and find the difference between the two atoms involved. So if the electronegativity difference is greater than 1.7, it's ionic. If it's between 0.5 and 1.7, it's polar covalent bond. And if it's less than 0.5, it's non-covalent bond. So If we look at LiCl, lithium chloride, this is ionic. What would be PCl3?
Polar covalent.
Polar covalent. Exactly. So phosphorus is 2.1, chlorine is 3. That's a difference of 0.9. This is polar covalent. Magnesium oxide. You should just be able to look at that and immediately go ionic. We have a metal and a non-metal. They're on opposite sides of the periodic. This is most definitely ionic. Carbon with 4 hydrogen, methane. Carbon is 2.5, hydrogen is 2.1, that's a difference of 0.4. This is non-polar covalent bonds. Nitrogen with 3 fluorine.
Polar covalent.
So nitrogen is 3, fluorine is 4. So that would be polar covalent bond. Alright, I'm going to begin. Next PowerPoint. But I'm not going to do it too much. Did I give y'all this one? I don't know if we want to practice with fluid style structures. We're going to do geometry later. Or tomorrow. And might as well do all the geometry. And I think it's front and back to the same one. And I just realized, Carlos, I didn't give you one. Sorry, I have 3 still memorized in my head. And also I have to remember to ignore but. Which is going to use this one. Alright. So we got some practice in yesterday. Let's go over the rules. So there are several techniques on doing Lewis structures for molecules. Personally, I just prefer the wrong way of just hacking it until I get an answer. Which is not the correct way of doing it. Because the correct way makes it easier sometimes and sometimes not. So count up the total number of valence electrons. Connect all atoms with single bonds. in order for it to be bonded together, there has to be at least one bond. So you can go ahead and just connect all the atoms together. There has to be at least one bond between all of them. Multiple atoms usually go on the outside. Single atoms usually go in the center. As we saw yesterday with N2O, that wasn't the case. Y'all all put oxygen in the middle, and it turned out nitrogen was actually goes in the middle. The thing is, the atom with the least electronegativity usually goes in the middle. Whatever atom has the least electronegativity almost always goes in the middle, except for hydrogen and carbon. Carbon always goes in the center. Hydrogen always goes on the outside. So, I would write that down. En, lowest En goes in the middle. Carbon always goes in the center. There's no exceptions for that. And hydrogen always goes on the outside. And then you complete the octet on the exterior atoms, with the exception being hydrogen because it only has 2. And you should have no unpaired electrons. Why is the electrons paired on the molecule? So remember I taught y'all when doing Lewis structures for single atoms, I told you don't pair them up, try to spread them out as much as possible. Why do you think they are paired in the compound though? Let me give you an example. Let me load up the 3D shape. Alright, so we see a pair here and a pair here. So this is like water. Why? Let me actually just remove one. So this could go on one side, so you can have a single electron by itself over here and a single electron over here by itself. Why are they paired? What does this remind you of? What does this look like? A dumbbell? What? When did I use the word dumbbell? What does that shape remind you of?
It looks like
P orbital. Do y'all not remember the p orbitals? And how many electrons can go in a p orbital? A spin up and a spin down. Whenever they, due to Pauli exclusion, whenever they interact and join together, y'all remember the musical video I played for y'all? If y'all can remember them lining them up. These p orbitals overlap each other. More advanced science. I don't ever do this, but there's something called, and I do not remember it from college, but I know it's also taught on a high school level. Pi bonding and sigma bonding. And I do not remember which. If we have 2 p orbitals that are next to each other, they bond like this, then this is a p orbital. A pi? No. It would be a sigma. No, it wouldn't. It would be a pi. Because whenever they merge together, they merge looking like this, and that looks like a pi. So this would be pi bonding. And when you have the two p orbitals bond like this, where they come together like that, this is known as sigma bonding. I never taught that, and I probably won't teach it. Yeah. So you have an S, so this is an S and a p orbitals, direct head-on collision, sigma bonding. And then we have pi bond is whenever they overlap like this. Sigma bonding is way stronger than pi bonding. So, we're going to pair up all the electrons. So, due to Pauli exclusion and other things, they end up being paired off. And then we check valence electrons match with step 1. All atoms except hydrogen have octet. If not, try multiple bonds. And then if we have any extra electrons, put them on the central atom. This method I don't really like. Basically is guesswork. I like actually keeping track of all the atoms, all the electrons from each atom. So carbon tetrachloride, total valence is 32. Central atom is, so chlorine has 7. There's 4 of them. So that's 28 electrons for all the chlorine, then 4 for the carbon, giving us 32 in total. Carbon always goes in the middle. We're going to put single lines for all of them. And then fill the octet on each of the chlorines, check the number of valence until we get to 8 on each of them, and then add more bonds if we don't, or stick extra electrons until we do. Again, I don't like this method. So let's work on some examples. So C2, H2. Try working on that. This is acetylene, by the way. So remember, carbon always goes in the middle. Hydrogen always goes on the outside. You want to get an answer?
Dude,
What'd you get?
I got the carbon triple bond and single bonds to the hydrogen with the hydrogen coming on.
So, 4 there, 4 there, 1 there. So we can immediately just connect and pair off. So we have single dots. We can replace those. And then replace these two with a line. And replace these like this. So, around this hydrogen, we have the 2, the line. Around this, we have 1, 2, 3, 4, 5, 6. We have 6 around this, so this is not completing the octet. And we have 6 around this one, so not completing the octet. We can share these 2 electrons with this carbon, and share these 2 electrons with this carbon, making a triple bond. So pairing up these 2 electrons and pairing up these 2 electrons, we recheck. 2, 4, 6, 8. And 2, 4, 6, 8. The carbons now satisfy the octet rule. So this is the correct formula. There's a triple bond between the 2 carbons and single bond between the hydrogen. If you really, really want to get super, super advanced, you can do orbital method. So there is a sigma bond between the 2 carbons, and there are 2 pi bonds where these orbitals here match up. So here's supposed to be showing 3 p orbitals. So this is 1 p orbital with another p orbital mixing. Here's another p orbital mixed with this. So this is sigma because it's a head-on collision. These are pi bonds because they're parallel with each other. And then we have a sigma bond here and a sigma bond here. Again, sigma bonds. You don't need to know sigma and pi bonding, but this is another way of drawing it using the orbitals. Sigma is way stronger than the pi. But I thought it was neat to know, to be thinking back on orbitals. Is this... Which bonds are polar?
Carbon or hydrogen would be.
So carbon is 2.55 and hydrogen is 2.2. So that would be 0.35, which is less than 0.5. So this is nonpolar. The EN difference between carbon and carbon is obviously 0. So these are all nonpolar. So there is no polar bonds in this molecule. Even if these were polar, because of symmetry, this whole molecule would be nonpolar. But we'll look at symmetry when we actually go over geometry. By the way, don't write water like it does on the bottom. And that is correct for Lewis dot structure. But we'll see later on when we go over geometry. Water is bent. Put the hydrogen, the two hydrogens closer together to show it's bent. We'll learn, like right now, y'all don't know geometry yet to know that it's going to be bent, but we'll get into that tomorrow. So so the diatomic elements, you have to remember where they're at on the periodic table. We got hydrogen, and we're going to have nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. This L shape. So nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. An L, and then hydrogen up there too. What are all the bonds on each of them? So let's go through the diatomics. H2. It would be just hydrogen bonded with hydrogen. This has two, that has two. So it's a single bond. Nitrogen. So N has 5. It needs 3. This one needs 3, so you can link up all these. It'll be triple bonded with 2 electrons out here. It'd be a triple bond. O2 has 6. Again, each oxygen needs 2, so we can connect them together for a single bond. I mean, a double bond. So they're double bonded. Fluorine. What do you think fluorine is going to be? Single, double, or triple? Actually, what do you think all of these will be? Yes. So they have 7 electrons. So it just needs 1. So when we connect it over here, they're all going to be the same shape like this. They're all going to be single. Alright, let's practice with probably the most hardest Lewis dot I've came up with. P2O5. Let's first talk about where the phosphorus and where the oxygens are going at. So we have phosphorus and a phosphorus, and where would the 5 oxygen go?
spread.
So what? 3 over here and 2 over here.
Oh. Doesn't look right.
Good. You notice it doesn't look right. So I'll give you a hint. To get you started with. It's going to have some structure. The symmetry in it, or another way of writing it. Like that. It's going to connect like this. If you were to, so basically if you started out by guessing it looks like this, you'll find that there's no way to balance this. Because let's count how many, let's count how many are around this phosphorus. So there's 2, 4, 6, 8. This phosphorus has 8. These have 7. If I attempted to pair off, I would get the wrong count. This phosphorus has no more to give to this. So you can see that this is already full, and there's no way to give these oxygens their octet. So you can immediately rule this out as being possible. So try working on this problem. No. Yeah, I'm out of time. Try working on it for tomorrow without Googling the answer. But this was a good guess by putting the 2 phosphorus. It's just that whenever you look at how many bonds it has, because remember, there's going to be at least 1 bond between all the atoms. But when you put at least the 1 bond between it, this gets 8 and these have 7, and there's no way to connect them up.
Between the two, like I knew that it wouldn't be 3 and 2, but I didn't know it was going to be like.
Well, you know, phosphorus has to go in the middle because it has less N. But the only way to do it is also put an O in it. What you have is really just this. You have PO3, 2 of them bonded together, and they share 1 oxygen.